Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, we are diving into Lab 3. In our previous lab, we learned how to use Vivado's built-in IPs. However, as developers, we can't always rely solely on pre-made components. That's why today's theme focuses on how to package your own custom RTL code into a professional IP core, and utilize the IP integrator for graphical block-based circuit design. We have already covered the basics of tool usage and how to instantiate internal IPs. Today's Lab 3 serves as the critical milestone bridging our path to future SoC designs. This is because, from Lab 4 all the way through Lab 8, nearly every single operation will be conducted right inside this graphical interface known as the IP integrator. Here is the outline for today's session. Before we begin, please ensure that you are fully prepared. For detailed content, please refer to the pre-lab course. There are two core objectives for today's lab. First, we will master how to package an IP. Second, we will practice utilizing the IP integrator, which is what we call a block design. Think of this process like solving a jigsaw puzzle where we assemble a hardware system by simply wiring components together instead of writing lines of code. Today's example circuit logic is identical to Lab 1. We use 8 slide switches to control the LEDs, and we've also retained the forced override control feature, where long pressing the left push button temporarily turns all LEDs on, and long pressing the right one turns them all off. Since the underlying logic remains exactly the same, our main practice today is to learn how to package it up into a reusable core. Now, let's introduce the block design interface in Vivado. To put it simply, think of this place as the assembly factory for your FPGA. These blocks you see on the screen are called IPs. Whether it's a custom package design of our own, or a processing unit like a CPU, they all appear here as individual modules. Now, pay close attention to these thicker lines. This is the AXI bus. It acts like a high-speed system highway, responsible for routing data and commands to their correct addresses. What's even better is that we can use the automation feature in the top left corner to let Vivado route the connections automatically. It's crucial to realize that the diagram you see on screen will ultimately be translated into Verilog code by Vivado. So, you're not just drawing pictures here, this is visual programming. This perfectly embodies the essence of modern SoC design, modular development and graphical integration. Here is the schematic diagram showing the internal logic of our IP. As you can see, we have slide switches and push buttons configured as inputs, and the LEDs designated as outputs. When packaging an IP, we must be absolutely clear about which ports are inputs and which are outputs. If the interface definition is incorrect, the external signals won't be able to route into our circuit properly. Today's workflow involves quite a few steps. First, we will take our project from Lab 1 and package it to generate our very own custom IP. Next, we'll open up a brand new project for Lab 3, instantiate that freshly packaged IP, and complete all the wirings inside the block design interface. Finally, we will run the logic synthesis and generate the bit stream file. Master the sequence, because this entire workflow is the industry standard SOP for developing large-scale projects in the future. You can download the required source code examples for this course from the link provided. Let's start the project now. First, open up Vivado and click on Open Project. Navigate to the folder, open up Lab 1, and select the corresponding XPR project file. Next, click on Tools from the top menu, and select Create and Package New IP. Choose Package Your Current Project here. Once completed, the Package IP window will appear, and you can click here to maximize it. First up is the Identification tab, which contains IP-related settings including the storage location, IP name, and description. Next is Compatibility, where you can review the information regarding the supported target boards. Moving on to file groups, this displays the storage paths for the source files used. If there are ever any file loading issues, you can manually modify them right here. Next, we have customization parameters, where you can configure custom parameters for your IP. Now let's check ports and interfaces to double-check the configuration of the IP's input and output ports. Then comes addressing and memory. If your IP is instantiated inside a bus system, you can configure its base address mapping here. Next, let's look at the customization GUI, which shows exactly how the IP block will visually look once it is instantiated. After verifying that everything above is correct, we can click on Review and Package, and then click Package IP at the bottom to complete the packaging process. Now, head over to File at the top menu, and let's create a brand new project. Enter the project name lab3_example. Select RTL project just like before, and check the box for Do Not Specify Sources. Choose the ZedBoard as we always do. Now, we are officially entering the block design phase. Under the IP Integrators section on the left-hand menu, click on Create Block Design. Once complete, the IP diagram workspace window will open up. Now, open up Settings right beneath the Project Manager menu on the left. Navigate to the repository subitem under the IP category. Click the plus sign button here and select the lab1_example folder we just packaged. Next, we can maximize the IP diagram window pane. Click the plus sign button to instantiate our IP core. Type demo into the search bar. And double-click to open demo_v1_0. What you see now is exactly the Lab 1 design we packaged earlier. We need to select individual external pin ports one by one, and click Make External from the top menu or right-click menu. As you can see from the current screen, after finalizing the IP block routing layout, we click Validate Design on the upper toolbar. This step ensures that the entire block design system is completely free of errors. Next, minimize this pane and head back to the Sources window. Under the Design Sources hierarchy, locate the design_1 block file, right-click on it, and select Create HDL Wrapper. Make sure to select the option Let Vivado manage wrapper and auto-update. Once finished, you will notice that the tool automatically generates a top-level Verilog file that instantiates all the IPs within the block design. Next up, we need to add the physical constraint file. Click on Add Sources again. Choose Add or Create Constraints, and click Create File. Enter the constraint file name demo. Heading back to the sources page view, you will find the newly initialized XDC constraint file here. Simply copy and paste our pin constraints template directly inside. The next step is circuit synthesis. Click on Run Synthesis from the left menu. Once finished, click OK on the dialog box to launch the implementation process. After implementation completes, go ahead and click Generate Bitstream. Once the bitstream is ready, select Open Hardware Manager. To enter the hardware workspace interface. Once you've entered the workspace, please follow the diagram to connect the ZedBoard using cables and turn on the physical power switch. At this moment, the green power LED will light up. Now, click Open Target at the top menu and select Auto Connect. Then, click on Program Device above. The blue configuration LED on the ZedBoard should light up now, and our custom counter circuit will begin executing immediately. Here is the final demonstration for Lab 3. Following a successful hardware program flash execution, you should notice that the designated LEDs toggle dynamically in response to flipping the slide switches. Long pressing the left button forces all LEDs to turn on temporarily until released. While long pressing the right button forces all LEDs to turn off completely until released. This successfully demonstrates that we have transformed our custom RTL code into a modular, reusable IP component block. Finally, here is a quick preview of our next lab. We are going to embed an actual processing brain, a CPU, right inside our FPGA. Starting in Lab 4, we will no longer limit ourselves to writing Verilog hardware code. Instead, we will begin developing firmware in C logic. We will learn how to build a complete SoC architecture and understand a critical core concept, address mapping. You will discover that what used to be complex hardware register controls becomes, at the software layer, nothing more than issuing simple read and write commands to a specific memory address pointer. This is the fundamental underlying mechanism that powers modern smartphones as well as autonomous driving systems. I'm Albert. Thanks for watching, and I'll see you in the next class.